So I stole this title from my own paper that I had published in IEEE, and we were making an argument why we need an earth science informatics technical committee in IEEE. So basically moving from data to knowledge, role of data science and informatics. So all this is a pretext to basically talk about our group, which is the data science and informatics, what we do, our rationale for the research we do, our portfolio. So this is going to be a fairly high-level talk. It's going to be a bird's eye view of our activities. And if there are any details that you want to know, catch me later. Manoj's here, so we can definitely drill down into specific projects and go over details. Just a big bio. I joined NASA about 3 years back. I was the principal research scientist at the University of Alabama for a few years. I also led the informatics group in Oak Ridge National Lab for a year. And then I joined as a DAC manager. I manage one of the data centers now. One of the key roles that I play right now is I serve as a strategic advisor to the Earth Science Data Systems Program Executive at headquarters. We're looking at how to evolve the data systems towards the future. And I have a particular project that touches it. I should probably have a slide. You guys should know all this. This is just a basic background on what is informatics, what is data science. As you know, informatics is basically the study and practice of dealing and managing information. But for us, it's not just information. It's basically data and knowledge. Data science, obviously, is a new word that gets thrown around. When I started, it was called data mining. There's a person called Osama Fayyad who came up with this definition in the 1990s of KDD, knowledge discovery databases. Fundamentally, it's nothing very different. It's extraction of knowledge from data. But what is interesting now is the practitioner of a data science. That definition has changed a little bit. So the practitioner of a data science doesn't not only have to have knowledge of the problem area and the domain and the analysis skill, but now needs to have software and system engineering skills, because now you're looking at scales that are much larger than single analysis. You're looking at large scale analysis of data. So that's kind of an interesting nuance of data science here. So this is our charter. This is data science informatics group's research and development charter. So we focus on informatics and data science components on 2 life cycles. So we look at the scientific process in terms of 2 life cycles. The first one is the data life cycle, which is the foundational life cycle, which is the whole process of acquiring data from instruments, going through the process of doing CAD/VAL, the processing, staging, data stewardship, to archiving and distribution. That's our foundational data lifecycle that we look at. What wraps around it is this whole process of scientific analysis, the process of knowledge generation. So there are 2 of these life cycles, and we look at data science and informatics components that impact these 2 life cycles. So why do you think we as a group are important? There is this fairly cliched statement that you hear all the time, that data is the new oil. I kind of like it. I mean, part of, says 2 things. One, data is valuable. And I would kind of argue that, even science data, we really don't exploit data and the information that we collect around science data effectively. And the second thing that you can extract from this statement is that, like oil, extracting information or knowledge from data is not a trivial process. It's actually a fairly hard process. So it's dependent on us to figure out how to extract and utilize data effectively. The graph on the left is showing the only thing that remains the same for us is change. We are always impacted. We are impacted at 4 different factors. you have the changes to the data, the rates at which we are collecting the data, the types of applications we want to do with the data, and the complexity of the data is changing. It changes every time we have a new sensor that goes up. The policies around the data is also changing. We started with open data policy, but now we are looking at making our source code available. The end user expectations of using the science data is also changing as people are getting used to iPads and iPhones. The expectations of how they interact with the data, do analysis is completely changing from when I started doing science. And the biggest contribution to this change is obviously technology, right? It changes every 2 years, we have something new, and then everyone has to adapt. We have to adapt our data systems, information systems around it. So if you look at this Gartner's hype cycle, you can see all these new technologies that are coming. And part of our job is to look at these technologies that are coming to figure out how are they going to impact our systems 2 years down the road, 4 years down the road. So if you look now, you have machine learning, which has reached the peak of inflated expectations, right? It's got the most hype right now. I've done a lot of work with ontology and taxonomy work. Now it's hit the trough of disillusionment, which is right because it doesn't scale that well. We all realized it. So there are some interesting stuff that's coming up in terms of these new technologies that we have to be aware of. Blockchain is getting there. So this is our DSIG portfolio. I've divided it into 2 parts. There is an operations part, which is the data center. The data center that I manage is called Global Hydrology Resource Center. There's also a SIPS, which is the Science Investigator-led processing system. We run a SIPS for answer to instrument. And then we have our R&D portfolio. So we work on different levels of granularity, from algorithms to applications to full systems that we can use at an enterprise level. The things that we work on are informatics, which are looking at processes, practices, protocols, and standards, but also machine learning and deep learning, semantics, knowledge graph work, and the data system evolution itself. So here's a short overview of my DAC here. It's a Global Hydrology Resource Center. For people who don't know what is a DAC, DAC is a NASA-funded entity that is responsible for processing, archiving, and distributing any data that's collected off the US satellites and fleet programs. And DACs have been really successful in archiving and distributing these data sets. They've distributed millions of files over these years, and these files have made known contribution to the science community or science community. So here are some metrics that's showing this. So there are 12 NASA DACs, and they all have a thematic focus area. So they provide data sets according to a specific science theme, and they serve a specific science user community. Right. So 3 years ago, I took over managing Global Hydrology Resource Center. One of the first things we did was we evaluated our holdings to see what we have and whether our holdings align to what our mission statement was. And our data holdings really didn't align with our mission with the mission statement at that time. So we revised our mission statement to focus now on, instead of hydrology per se, but also on hazardous weather, and look at all the processes associated with hazardous weather and associated applications. So this analysis was done looking at the other DACs in terms of the thematic area of expertise that they provided, and also looking at the core expertise that exists within Marshall. So it was to align our mission statement with the science expertise in our SD11, and also to find a niche area that didn't exist in the other gaps, that not had the overlap. So that was the major realignment of the mission statement that we did. So what we serve, these are some highlights of some of the major data that we serve. Lightning data, we've been ingesting and archiving lightning data since 1990s. We started with, I think, OLS line scan sensor that was on the DSIG satellites, which is basically just a sort of visible, it's like photograph at night, so you can kind of see flashes. And then the follow-on instrument was the OTD, so 1995 to 2000, and then the trim Liz, which was from 1998 to 2015. So when they designed the trim Liz instrument, they designed a backup instrument. So that backup instrument was this flown on the International Space Station recently. So now we will have data from ISS Liz. So this is the Liz sensor now on the space station. So we'll have the data, at least the beta version starting June. It's really interesting. A lot of interesting work has come out of the data set, like climatology that was created looking at Liz. There's a really interesting TED Ed video where they showed the maximum lightning strike occurs in Venezuela. There's a particular lake in Venezuela where we have the highest lightning density of strikes. So, the things that we obviously hold the data that comes from vision, but we also archive derived data that comes from the user community. So, as a DAC, we also work with the user working group to bring in data produced by a community that is linked somehow to our original data set, but is useful for our community in terms of supporting their science, so that there is a place for long-term stewardship for important data sets. We also serve passive microwave data, starting from 35 years worth of data, starting from MSU all the way to Ansari. This is the other category of data that we archive and provide data stewardship for as field campaign. So we hold field campaign data for hurricane science for different field campaigns in the 1990s. HS3 was the latest one that we provided data stewardship for. Also for GPM ground validation field campaigns, we provided, we are the archive. So the field campaign data tends to be very different from mission data. It's more heterogeneous, it's more episodic, it's probably what you call more long tail of science. The stewardship that you need to apply to it is very different from what you need for a mission-based data sets. So different processes are required. In fact, Monil has led the whole revamping of our infrastructure. We have tried to automate a lot of the processes of data publication within an archive to make it more efficient so that we can actually publish a lot more data into our archive and distribute it out. That's been a major effort last year.
So is it field campaigns in the atmospheric sciences?
Yeah.
How much total data do you guys have as a company and as a product, so things like that?
I should know these numbers. Our holdings are very small. What is our total holdings?
Maybe around 40 terabytes.
40 terabytes.
For example, yeah, terabytes.
Yeah. We are like the smallest DAC, one of the smallest DACs in the world. This is I'll show you some current and recent projects from our portfolio. This work was started by the Obama administration. It was out of OSTP. So the goal here was to make all the climate-related data sets from different federal agencies discoverable. So as NASA, we were in charge of the process of getting all the data from different federal agencies into a catalog and publishing the catalog. And there were 9 thematic areas, and different federal agencies were leads of these thematic areas. They helped in curating the data sets and identifying the data sets, and we were in charge of making sure that the process worked and all the metadata was correct. So we were quite successful with this. The follow-on to this activity is called PrEP. So whereas CDI looked at just making the climate data sets discoverable, PrEP was looking at how do we make now the climate data more accessible and usable. So we're looking at machine APIs for particular data sets, and then trying to build a platform where people could come and do analysis. They were looking more towards people at state and local government level who were making decisions, and they wanted to provide them data in a manner that they could actually use. They wanted to provide them information in a manner that they could use and not just the data. I think that's been the biggest challenge with the climate data, as you know, that it can't be consumed that quickly and easily by people who need to make decisions down the chain. So the PrEP was released last year, the platform was released last year, and it had partnerships from Amazon, Google, and different agencies. So one of the things that came out of this work, we were so successful in going and looking at different agencies' metadata, their processes, and helping suggest ways to improve their metadata records and quality of their work, quality of the metadata records. We'd always tell them that we know how to do metadata records. We've been doing it for a long time. And when we went and looked at our own catalog, we found lots of issues, which was rather embarrassing. So they said, hey, we've done such a good job with other agencies, why don't you go fix our own? So this is a project that's ongoing right now, where we're manually going through about 7,000 collections, and an example, granule also per collection, and trying to find, look at each field to fix any issues. But more importantly, also developing rules on the way that could be automated, so that in the future, as new metadata records are going in, these rules could be applied to fix existing problems. This is, a major project that is, it's called Cumulus. It's back in the cloud. Where it's basically trying to build a cloud-based data ingest, archive, and distribution system. The goal here is, trying to figure out whether we can use commercial cloud infrastructure for our data systems in the future. Based on the future missions, the rate of data sets that we are getting, we know that the current infrastructure cannot support it at the current budget levels. We have to find new solutions for it, and there's no two ways about it. So the question is using a commercial cloud infrastructure the way to go, whether we can leverage that infrastructure and provide same service, if not more, at a cheaper cost. So there is an effort that's going on looking at cloud quite extensively. There are different aspects to it, and this is one of the components of it. There are 13 different projects looking at cloud. This is one of the core components. So the goal here is to develop a functional, lightweight ingest archive distribution cloud native framework. So this is where, why cloud native? Because we want to leverage the AWS infrastructure as much as possible and not reinvent the wheel. And the lightweight is, if we leverage the infrastructure, then we have operationally very little code to maintain. That reduces operational cost down the road. We're trying to minimize the footprint of the code that we have to maintain to run the system through. So the approach is to build a working prototype, which we have right now. We want to show that this prototype can handle different data streams in nominal and not nominal mode. When things go wrong, can we do this without it failing completely? And we're using a phased approach. We are going DAC by DAC, looking at specific data streams per DAC so that we can kind of understand how each DAC operates. And obviously trying to get them to buy into this notion that we need to move to the cloud. This might be a solution. So the we finished 2 phases. We started with GHRC because we were like a small DAC. We understood our holdings. We started with that, with the field campaign data. We've just finished phase 2, which was the LP DAC. We got Modus and Aster data sets on the cloud using the ingest archive system. We had our own evaluation whether we need to proceed with this or not, and we decided yes, we are successfully. Most of the functional tests passed. And now we're going through this code convergence re-architecture. And this is where working with Amazon, the drawback is, they change so fast. So we started, I got the dates wrong. We started last year. We were using something called data pipelines. And after phase 1, we had to switch to Lambda. And now after Lambda, now we're looking at something called step functions. So every phase they've come up with a new infrastructure service that replaces something that we already built. And they've done it better, so why should we try to write our own? So that's one of the key activities that's happening right now. This is the concept of how we think it will work. This is an operational concept. So we have something called NGAP, which is the NASA compliant cloud services, which will take care of all the security policies sitting on top of Amazon. There will be multiple instances of Cumulus running, and one way to look at Cumulus is just a workflow engine. And there will be a Docker repository, as you were saying, that will be shared by DAC. So there are common steps that the DACs are now developing. It could be reused across the DACs. And the workflow would be a set of recipes that will be run. So the idea is simple. The hope is that the engine itself is really lightweight and small. The specialization for each DAC is within the Docker repositories that they provide as containers. And maybe this thing could be reused to do processing and different kinds of stuff, because all it's doing is sequencing different steps. And there are certain core functions that the DACs have to do, like publishing to a catalog and reporting metrics. So those components would be a part of the Docker repository that they could leverage. About a year and a half back, I was involved in this partnership with the commercial cloud providers. One thing that we realized is that different cloud providers are consuming our data more and more to do analysis at scale. They were going to individual DACs and grabbing their entire archives. So we decided, hey, let's do a partnership to figure out how do we efficiently enable access and transfer of the data to these different cloud infrastructures, rather than have to address Google ones and then Microsoft and Amazon again. And so we worked with them, and they gave us a set of use cases in terms of what they think. They didn't give us their whole business model, but they gave their use cases on how they anticipate, how they have used NASA Earth Science data, or how they anticipate using our data sets. And we use those use cases to develop a set of requirements, and then we use those requirements to test our existing data systems to see what we have, where the gaps are, and what we need to improve. And then we also turned it around to make it more of a generalized recommendation that we submitted to USGO, which is like an interagency government body that works together with, and they deal with Earth science data. So this was an interesting partnership to work with them to see how they are looking at stuff. The kind of user support they want. Typically a DAX user support is more about looking at science questions or how to open up a file. But the user support they want is like network bandwidth. They want to talk to engineers, not user support services. The kind of metadata that they thought was important, we as DACs would tend to overlook it. They were really interested in versioning because they want to know when the things have been updated. They want to automatically figure that out. They are looking at things, they want subscription-based notifications. so that they know when things have changed or a new data set has been added, so their systems can automatically go grab it, they don't have to do it manually. They also wanted to a way to pull all the metadata information from our catalogs so that their systems of ingesting and archiving would run at scale. So they were not really interested in doing simple, 5 queries and get 5 results back. They wanted the whole listing of all the granular files that their systems could run through. So it was an interesting exercise to go with them and see how they were approaching it. They were kind of our power users that we never really encountered before. Unless you are like a computation center, then you're probably equivalent to that. This is, Nikunj should be very familiar with this particular project. So this is our AIST project. It is called Dark Data. The goal here was to utilize information sources that we tend to ignore or never utilize beyond their original needs. Things like metadata. Can we utilize metadata to do more things like relevancy ranking, browser imagery? Can we utilize browser imagery to do content-based image retrieval? But the science need was, how do we enable analysis and visualization of events? So events is an instance of a phenomena for a given space of time, right? So we have hurricane is a phenomena, and maybe Katrina is the event, right? So how do we build systems that allow users to automate exploratory analysis of events in a easy manner without having to know too much about the data or the data systems? And in fact, I would argue that the current data systems are not really suited for this kind of analysis. So what we built was this smart middleware, which consisted of a data curation service and a semantic rules engine. So what the data curation service provides is if you give this service a phenomena and space-time location, it will then give you back a list of relevant data sets that a user needs to study that particular phenomena. And it also goes down not just to the data set, but also down to the parameter. So it tells you within this file there are 18 parameters, but only this particular parameter is what you are really interested in. And that is tied with the semantics rules engine that was built by RPI. So that would then decide, okay, based on the data, the phenomena and the data set, it would decide, okay, what kind of visualization or analysis plot you can run on it. And that was tied with Goddard's Giovanni tool. So this is an example, a particular, and we could actually there is a EONet database of events. So you could pull in events from the EONet database, and that would trigger off a workflow which would show visualizations of the different variables. And it will also show you the data set as well as the different visualizations per parameter. So if you were not interested in doing fully automated, you could kind of select the pre-filtered list that this middleware will provide you. So that was the AIC project that Nikunj was supervising for us. This is an ongoing project that I'm working with Jia Zhang, I guess, who's here in this building. This is trying to build knowledge graphs from unstructured sources. So one of the things that is heavily underutilized are publications and reports. We want to figure out a way to extract entities from these publications and reports and put them in a graph so that we can actually mine these graphs. So at the lowest level, we can use those graphs to improve searches. We can improve searches on our data sets and help recommend data sets or services that people would have not thought about based on these graphs. But at a higher level, what we really want to figure out is can we discover new knowledge that's there in these papers that we cannot link together because we cannot make so many connections when we plow through thousands and thousands of papers. So the goal of this graph, this project is to put together this graph which connects hypotheses, data sets, variables, methods, findings together in a manner that we can actually do machine-based querying on it. So we've been working for about a year. We're really struggling with this step called the semantic entity identification. It's very easy to extract entities, but very hard to figure out what does entity actually mean. The data set, trying to identify whether it's a data set or not has been a non-trivial problem. We're going through different approaches of this. We've done some, our test cases, we are working with a domain expert who gave us his publication list, which is like 355 papers focused around airborne dust. So we are focusing on that to see what can we extract from them, and just doing shallow analysis, looking at all the variables that come out of it, the data sets that come out of it, so that we can evaluate the quality of the result. But even with this shallow analysis, it's kind of interesting, and I showed it to the expert. He's like, oh, I can see the hypothesis from the papers based on the variables that you extracted right now. Like, you have to have wind speed, surface albedo, surface temperature. These are the key things that are important for airborne dust to occur. And then he was looking at the instruments. He was like, oh, it's not a surprise that Modus is the top instrument for this kind of work. But he was also like, hey, Miser is not there. And he argued that, I think I know why Miser is not there, because it's so difficult to work with. So there are interesting things even with this shallow analysis that you can glean from publications. But the goal would be, once we have a graph, then we can find things that are, that are there in the papers, but nobody's kind of made those connections. So one of the aspects of our AIC work was to look at content-based image retrievals. We were looking at what we had proposed, different index-based approaches, and I think Mike Little was like, hey, your methodology that you proposed is too outdated, you need to look at newer techniques. So then we started looking at deep learning methods, especially convolution neural network. So this was our first foray into using CNN. We wanted to test whether it's something that we can actually pursue further. So this test case, we said, okay, let's look at browser imagery and let's try to figure out whether we can identify different kinds of phenomena from the browser imagery. So we looked at dust, hurricane, smoke, and others as examples. And the results were really promising. I think we were kind of impressed that, there is some potential here. So, and most of you already know this. I mean, I should be saying all this. You all know deep learning. Unlike traditional mining or traditional classifiers, one of the advantages of deep learning is that it learns the features itself. That was the biggest drawback with classifiers, is you had to have domain knowledge, and you had to have knowledge about the data to build a feature vector. If you could not construct a feature vector, it didn't matter which classifier you used, right? I mean, you could use SVM or regression, you still get crappy results. In fact, there's a paper, KDD Cup, people who won were the ones who understood the problem. It was not the ones who had the most sophisticated classifier. So one of the nice things about CNN is, it actually removes that step for you. It actually tries to learn the features for you at different stages as it goes along. We're applying the different convolution filters, and at each stage, those convolution filters are learning, different kind of information. So you're going from simple edges to object paths to full objects. It's learning along the way. So after this, he was a grad student. He said, okay, I'll use this for his thesis. So he applied convolution neural network to identify transfer cirrus bands to study climatology, occurrences of where they occur. He got fairly good results. But again, in this case, the truth set was done manually. So that's one thing. You have to be with deep learning. It depends on the training set that you have. The larger the training set, the better results you'll get. This was done manually. He went and manually gathered the images and labeled them. This is the work that Manal has led with Dan Cecil, who's the hurricane expert. So right now, and the goal here is to use CNN to estimate the tropical cyclone intensity from satellite imagery. The current way of estimating tropical cyclone intensity from satellite is something called Dvorak's technique, which is subjective. You can have two analysts looking at the same imagery and give completely different results. So the question is, can we apply CNN, because it's a visual feature that they're looking at. Can we apply CNN and estimate tropical cyclone intensity? So this was done, and this is a perfect case for CNN because we actually have truth data. We have lots of truth data because they have wind speed data that a National Hurricane Center collects. And the setup was also quite easy because NRL has all the imagery data for the hurricanes too. So it was very easy to collect all this. I shouldn't say very easy, if you don't know. I can say very easy. And the precision that we got, the root mean square error that we got was much lower than what's there in the published literature with the different techniques. So this is actually really, encouraging that there are applications where this approaches could be applied. But the question is, are we clever enough to find problem areas where we have two data sets, or one data set could be used as training and the other data set could be used for doing this classification. So here's I don't know how to run this movie.
Maybe Rama, can you grab the mouse and just,
This one?
yeah, I think probably, you
Just
see the little,
the play button at the bottom. So Manal did put together a short movie to show, okay, once you train, the things we can do. So this is just looking at the model that does hurricane category classification. So you can go to the web and basically pick out any image of hurricane. So then you can give the URL to the strain classifier. And then it will tell you based on what it thinks is an H4 category, 95% confidence. So you could argue that that's fairly easy. That's an easy image to select. Maybe use something little. Okay, this is validating that yes, it was a category 4 at that time. Cuba. So, strong hurricane is fairly easy to identify, but what about something like a tropical storm, which is more diffuse, looks more like cloud? So this is an example of taking a tropical, this is Erica, and running it through the classifier. Let's say this is a tropical storm. So it works pretty well, I think, and as we gather more data, it could be improved. So it could be iteratively improved as we run it in an operational mode. So this is kind of a roadmap, what we really want to do with deep learning. We really want to leverage this hurricane classification algorithm and make it as an operational service, and maybe provide a web portal service for other clients to query, so that people can build the tools on top. We are trying to work with Marshall Sport to come up with a plan to do this. Hopefully within a year we can have something like this up and running. I am really interested to do more phenomena event detection. There is real value in this from the data systems point of view. We're trying to, right now you can't really search for phenomena within data, right? You can't say I'm interested in finding specific atmospheric rivers, which data sets have them. You can't really do that. I think building something like this would be really, really helpful, not just for the science, but for at least from the data systems perspective. And I'm really hoping that we can come up with some kind of collaboration with you guys here. That's all I have. If you have any questions, hit my cell and you can Slack me on NASA Slack. That's probably the easiest way to catch me.
Thank you, Rahul.